So, and this work recently, we've been thinking about both risk scoring for COVID, but also comorbidities. So these are other conditions that can show up in addition to the COVID diagnosis that can have potentially a sort of high impact on the outcomes that a patient has. So for instance, diabetes and obesity can have sort of high impact on the outcomes of the patient. And I'll skip maybe the details of the methods. You'll be familiar with, I think, some of the details of the methods that we use. But I think the interesting bit here is that in our analysis, we found systematic underdiagnosis for certain subgroups. So certain subgroups just had much sort of fewer recorded instances of comorbidities that we confirmed later that they had. And we found, or we believe that this is highly correlated with language. So particularly non-English speakers seems to be one of the groups that were affected the most. Again, more broadly in healthcare, I think we're more and more concerned about issues with machine learning being deployed in healthcare settings and how we're finding big differences across different groups after deployment. So within the machine learning world, the way that we like to measure the classifier performance broadly is often using something known as the confusion matrix, which many of you, I think, would be very familiar with. So here on the left, I'm showing a confusion matrix illustration for a binary classification problem. So in binary classification, the classifier is predicting one of two instances. It's either predicting 1 or 0, and the ground truth is itself also 1 or 0. And so if you take all combinations of those kinds of either predictions or ground truth, we can compute 4 numbers for either a data set or some data distribution. We can compute the true positives, which is the fraction of examples that are correctly predicted as 1, true negatives, fraction of examples correctly predicted as 0, and then the 2 kinds of errors that the model can make, false negatives and false positives for either incorrectly predicting 0 or 1. The important part of, and the reason I bring this up, is that I'll argue, mostly via example, but I think there's lots of good references on this, that many of the measures that we like to use to measure what our classifiers are doing boil down to some function of a confusion matrix. So the idea is if I want to understand or measure a classifier, what we most often do is take the classifier, compute the confusion matrix of the classifier, and then compute some function of the confusion matrix. Now, of course, if this function is straightforward, we may compute the function directly without necessarily computing the confusion matrix first. So the claim is really that you can understand many of the ways that we evaluate models as this kind of nested evaluation of confusion matrix and then some function of it. So many of you are already familiar with many of the examples. Accuracy in all of its weighted versions can easily be constructed as weighted functions of the confusion matrix. You're probably already familiar with precision and recall, which can be computed as ratios of confusion matrix functions and many other of these quantities. They're of course much more complicated, and you can make this as complicated as you like. I think the most popular of these more complex metrics might be F measure, which I think many of you might have seen before, popular in information retrieval, which can be computed as a ratio of, again, linear functions of confusion matrix entities. Now, beyond evaluating model performance, when we're interested in fairness problems, particularly group fairness problems, many of the metrics that we use can also be understood in a very similar way. The difference is, instead of a single confusion matrix and computing some function of it, often we compute confusion matrices for every group and then evaluate some measure across the different groups. So an example of this, for instance, is evaluating accuracy across groups and looking at the difference of accuracy across the different groups as a measure of fairness properties of a certain classifier. Functions like equality of opportunity, statistical parity, which again can be computed and evaluated and thought of, which would be the important part of this talk, as functions of the confusion matrix and seeking to equalize these functions across the different groups. And beyond these examples I've given, again, there's a large literature that has developed, some of it, of course, predating modern algorithmic fairness work, but many of these, again, can be understood directly as computing some confusion matrix of every group, and then looking to understand how these confusion matrices differ across groups, and in measuring this difference as a notion of group fairness. One key point, and one that will be important for a lot of the talk today, is the question of whether we can take one metric and expect that models that do well with respect to a certain metric will do well with respect to others. So what I mean is, broadly, metrics are developed to have similar properties. If you have, assuming a metric is a utility form, a bigger number means it does better. Or if you do 1 minus that, like a risk, a smaller number means it does better. So you expect that sort of good models roughly look the same, meaning if I measure respect to different metrics, I expect that the best models always look like the best models independent of the metric that I use. I think this can be untrue and is often untrue in practice. And in fact, the only cases where we can really guarantee that sort of all metrics will roughly look the same are in cases that are kind of degenerate special cases. But in most real data distributions, different notions of what performance means can lead to very different good classifiers with respect to that notion. An important bit for this discussion is that these, one way to interpret that, and I'll give an example in a second, is that metrics are in general not exchangeable. So doing well with respect to one metric doesn't mean necessarily that you're doing well with respect to others. And if you're interested in group fairness problems, then the question becomes, of the wide variety of possible statistics or metrics, what should you be looking to measure and equalize across groups? To really bring this home, again, an example that I like to highlight. So many of you, or any of you who have worked in algorithmic fairness, might be familiar with this example already. So this is work, I'm referring now to a ProPublica article, which analyzed this COMPASS algorithm, which was used to predict risk of reoffense, which a judge might use to, say, make a sentencing decision. And in algorithm development, the company that developed this, Northpoint, used calibration as the way they measured fairness properties, while ProPublica in the post-analysis chose to use false negative rates and false positive rates. And when they did the analysis, what they found, and I'll quote, is that Black defendants were twice as likely to be incorrectly labeled as higher risk than white defendants. Conversely, white defendants labeled with low risk were far more likely to end up being charged with new offenses than Blacks with comparably low COMPASS risk scores. Of course, this is a complicated situation with many moving parts. The bit that I want to highlight and what's maybe most relevant to my talk from this general line of work is here there are two instances of, say, building a model for one metric and then evaluating with a different metric and then finding that good properties with respect to one metric don't necessarily translate to the other metric. And so one way to try to address this problem, and the approach that we've taken to try to address this problem, is to take a look at the metric selection problem and see if we can improve it. So it's maybe somewhat early days in some of the work, but I think we've made some good progress. I'm excited to share. So the broad direction we've been calling metric elicitation. And the idea is we want to come up with strategies that can query stakeholders in order to quantify the utility. The utility here being some measure of performance of the model. So in particular, this would be especially important and interesting in fairness applications, as I'll talk about in a few minutes. So the rough idea is that there's an elicitation procedure. The elicitation procedure, which is the algorithm that we're going to develop, is going to construct a sequence of queries. These queries are designed to get information from stakeholders. We're calling them oracles for the purposes of this talk. The oracles or stakeholders give the algorithm preference feedback. And this feedback is used to come up with a measure of the preferences of the stakeholder. That's a good approximation. In particular, that's a sort of a quantification that can be used, say, as an evaluation measure, or can be used to train a model, a machine learning classifier, for instance. So there are a few bits in how to get this to work, and I'll go through some of the properties and important aspects of this. So the first is a bit on how one measures the stakeholders. There are, of course, many ways to do this. The approach that we've taken, first, we looked at directly trying to quantify for, say, different instantiations of models, how good or bad they were in various aspects. And as you might imagine, this is a challenging problem and not one that can easily be answered. What seems to be much more effective, and there's also literature in cognitive science and psychology to back this up, is preference queries. So asking preferences between pairs of objects, in this case, classifiers. You can much more easily get preference feedback and use this feedback as a signal for sort of what measures might make the most sense in terms of quantifying what the model is doing. And I'll show how we use this in a couple of minutes. The second, I think, key property is that there is a cost to queries because we're interacting with humans. And so too many queries result in fatigue. And so I'll summarize the goal of this broad line of work as trying to elicit a metric or a measure performance using as few queries as possible. In our case, specifically pairwise queries. Now, because of the time and sort of broadly set up, I won't be able to go into detail on all of the algorithms that we've developed for this problem. I will go into a bit of detail in a special case that I can maybe describe in a bit more depth and hopefully build some intuition about how these kinds of algorithms work to then lead to thinking about how we, say, address the fairness problem. So I'll spend a few minutes talking about how one can use some of these ideas to come up with an algorithm for eliciting linear binary classification metrics. So you should think of linear binary classification metrics as weighted accuracy, where the weights are, for instance, helping to quantify how important is a, say, false positive error versus a false negative error or vice versa. And so trying to get numbers for sort of the cost of these kinds of mistakes. And so these numbers you can think of as a linear metric in terms of the confusion quantities. And I'll talk about how the methods that we're developing can help address this question. So the first interesting aspect of this is instead of trying to understand or directly work with the classifiers, because the metrics are defined in terms of confusion matrices, we can directly reason about the metric in terms of confusion matrices. What this means for us is our goal would be first to try to understand what confusion matrices look like for, say, a particular setting with a particular data set or data distribution and then a classifier family. In particular, you can show some nice properties. So you can show that in general, for a problem, you can show that the set of feasible confusion matrices, which are sort of for a particular classifier class, the achievable confusion trade-offs that a particular set of models can achieve, can always be sort of described as a compact convex set. So a few things are important here. The first thing is, even though the confusion matrix for a binary classification problem has 4 numbers, you only need 2 numbers to fully describe everything that's going on in the confusion matrix. Many of you already know this. In particular, the reason is there are constraints in the confusion matrix. The true positives plus false negatives have to sum up to the fraction of 1s in the data set. And similarly, the true negatives plus false positives have to sum up to the fraction of 0s in the data set or the fraction of 0s in the population. And so this immediately constrains, sort of creates linear constraints between elements of a particular column of the confusion matrix. And you can show that you can fully describe everything in terms of 2 degrees of freedom. So here we use true positives and true negatives as the axes. You could also use false negatives, false positives, or other functions, pairs of functions as the axes. The second interesting bit, and worth emphasizing, is that not all trade-offs are achievable outside of degenerate cases where sort of things are perfectly separable. In general, due to noise, set of features, other factors, in general, there'll be a set of achievable trade-offs, and some trade-offs are just not achievable by any model in that particular setting. And so the first thing that we try to understand is a set of achievable trade-offs. So these trade-offs, again, end up describing a certain compact convex set. And if you're interested in linear metrics, then you can think of these linear metrics as linear functions in the space of confusion trade-offs. What's interesting and maybe important for some of the rest of the discussion is that, again, if you remember from, say, Optimization 101, if you're optimizing a linear function, in this case, a linear metric, with respect to constraint sets, in this case, a compact convex set, you can show, and we know that the optimal will always lie somewhere on the boundary. We may not necessarily know ahead of time where the optimal is. This is the sort of actual optimization problem we need to solve. But we know that somehow there's a representation result that's implicit, where you can show that the optimal of this optimization problem is somewhere along the boundary. And so the reason this is interesting in our setting is we can exploit the fact that optimal trade-offs always correspond to these tangent planes on the boundary of the feasible confusion matrices, because instead of searching for the best metrics everywhere in the space, which corresponds to, say, searching for the best trade-offs in all the feasible trade-offs, we can reduce our search to only searching along the boundary. So in a second, I'm going to describe a problem approach where we convert the elicitation problem to searching along the boundary, where each point along the boundary is some linear trade-off, to find the linear trade-off, in this case, would be the metric, that best matches the trade-offs of the stakeholder. So very quickly, I should show what these queries look like. So here, this is not our work. We're depending and using sort of existing work out of the HCI world, where they've developed tools to compare classifiers, to show stakeholders pairs of classifiers and get a sort of 1-bit preference feedback about which classifier is preferred between pairs. And so we use this as our main signal. Given this 1-bit feedback of preferences, we seek to find the trade-off that best matches the stakeholder preferences. So a bit of detail behind the scenes, but you can show that you can convert this problem into a one-dimensional search problem. So one-dimensional because, again, we've reduced our search space from the entire space to just the boundary points. So we can, again, show these or describe these as some unknown function, which is the function of sort of the performance measure at each one of the possible boundary points. So this draws out a function. We're unable to query at any point. We can do pairwise queries, and you can show that finding the oracle preference or the stakeholder preference corresponds to finding the peak of this function. So we want to know what is the maximum of this function using only pairwise queries. Again, many of you might already know that you can essentially adapt binary search as one reasonable algorithm to try and solve this problem. So for this example in particular, here's what it looks like. So I can, for instance, ask the stakeholder, I apologize, pairwise comparisons of, do you prefer classifier A versus B, B versus C, C versus D, D versus E. Based on these queries, I get 4 signals. So I get, in this example, better, 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 worse. And once I'm done with these queries, what I know is wherever the peak of this function is, it must be somewhere between theta C and theta E. And so I can restrict my search only to theta C and theta E, sort of the range between theta C and theta E, and then repeat the same procedure over and over again. So again, this maybe reminds you of basic binary search. So essentially behind the scenes, we're using a binary search kind of routine. So you can show that this algorithm has good properties. You can show that for this sort of linear trade-off setting, this simple binary search style approach has quantifiable oracle query complexity. So in particular, you can show that these parameters, A1, A2, which are the weights, are guaranteed to be epsilon accurate after log 1 over epsilon queries. And you can also show that unless you make additional assumptions beyond some of what the assumptions that we've made, you can't do better in this setting. We have done additional work, and I'll refer you to take a look at some of the papers, looking at various kinds of noise in the process and how we can model and mitigate it. So for instance, in most of our papers, we have a noise model where the oracle gives correct responses if you're comparing classifiers that are very different from each other. And if you're comparing classifiers that are very similar, there's some chance that the oracle gives you incorrect responses. So dealing with noisy responses from the oracle as sort of in the process of developing the algorithm. We've also extended this to additional cases. So I'll speak about the fairness instantiation of this, but there's also work on multi-class classification broadly and other kinds of more complex metric settings. So I'll switch gears a bit and in the same line, talk about how this idea can be extended to thinking about group fairness metrics and how one might elicit it. So the problem is, and the framing is similar. Some of the differences are, instead of a single metric for a single confusion statistic for sort of an overall population, we now have an evaluation of classifier performance for every group. In this case, again, a confusion matrix for every group. In order to quantify different notions of algorithmic unfairness or fairness violation, we define explicit fairness violation quantity. So this is defined as the difference between the statistics between every pair of groups. So again, you compute a confusion matrix per group. You take one element of a confusion matrix for group U and group V, and then you compute the absolute value difference. This tells you how much, say, the different, it quantifies, for instance, say, difference in false positives across groups. You can do this for all the entries of the confusion matrix. Taken together, the overall metric that we are going to look to elicit looks like this. So it has three main terms. The first term is a linear term, which is a linear function of some weights and a confusion statistics. So you should think about this as a weighted accuracy. So this is quantifying overall performance of the model across the whole population. The second term captures the fairness violation. So it includes the fairness discrepancy for each pair of groups and a weight for each of these fairness discrepancies. And this is summed over all the different groups. So this is a sort of fairness violation measure. And then we have a global trade-off, which has a weight between the sort of utility term and the fairness violation term, which tells us the global trade-off between the sort of utility and fairness for the stakeholder. And so in the elicitation setup, we're interested in eliciting three sets of quantities, A, B, and lambda here. So as you might imagine, this is somewhat more complicated than the standard setting. There's a lot of correlation across the different quantities we're eliciting. We need to deal with absolute values, so linearity gets lost. And so we need to use slightly different approaches to deal with this. As you increase the groups, you increase the number of parameters because the sort of size of B gets bigger. And so as we'll show, the query complexity roughly scales with the degrees of freedom and the parameters. The last thing I'll mention in the setup is that in the results I'll show and also in the papers, we directly tackled a multi-class version of this problem with K classes instead of just binary classification. So it's slightly more general than what I have discussed, what I discussed earlier. So in the work, we show, this is recently at NeurIPS, last NeurIPS, we show that you can take this overall problem and decompose it into a sequence of queries where you first elicit the utility term, which is this A quantity, which is the weight for the Oracle trade-off. And A has K squared degrees of freedom because there's a value in A for every entry of the confusion matrix. And for a multi-class problem, there are K squared entries in the confusion matrix. This is every pair of prediction and ground truth. And so there are K squared entries in A for weighting each of these kinds of errors. And so we need roughly that number of queries to elicit the first term. The second term is the fairness violation. Again, this has every pair of groups. So group choose 2 times K squared, and we need roughly that number of queries to elicit it. And then finally, there's a global trade-off term, which is, in this case, is just going to be a number, and then we need to set a constant number of queries to elicit it. So there's a bunch of, I think, exciting potential next steps along these lines, and very excited to maybe offline discuss with many of you about some of the potential directions. So in our work, we've mostly looked at binary classification. I think we're quite excited about other kinds of machine learning problems where many of these issues we think are extremely important and unaddressed, and interested in trying to address them. I've mostly talked about using these binary pairwise queries and sort of some set of trade-offs, mostly using sort of functions of the confusion matrices directly. I think there's a lot of interesting open questions in terms of perhaps richer query types. So for instance, auction queries or other richer kinds of queries. I think HCI plays a extremely important role in broadly in this line of work, because we need to come up with good strategies for interaction with humans in order to get signals about preferences. And so I think there's a lot of, I think, interesting work to do down that road. And again, we've been working on population effects, noise tolerance, and others. I think there are lots of interesting questions that remain unaddressed down this road as well. So that's what I wanted to share about the fairness work. I want to switch gears now and talk about a very different setting where metrics show up. I outlined at the beginning a little bit. Thinking about distributed machine learning, where there are questions about robustness, and we're interested in finding ways to address these robustness questions. So I would just take a half-second pause. Okay, so I'll go forward, since maybe take questions at the end. So as many of you know, there is increasing excitement about trying to construct and build machine learning models across data holders without explicitly sharing data. So this is partially motivated by privacy concerns in many cases, because sharing data explicitly clearly leads to privacy issues. Not sharing data can be part of a process for reducing a privacy threat. Of course, it's not enough. You have to do a bit more, but it's a good first step. And so broadly, there's been a lot of excitement. I mostly, in this line of work, I've been working with scientists and medical professionals, hospitals, thinking about training machine learning models without explicitly sharing data. So as you might imagine, there are a variety of technical challenges that show up when you're training with distributed data. So unbalanced data often causes havoc, site-specific biases of various kinds. Often when you collect data from different places and collect them in one place, there's a harmonization step that's critical in actually doing any useful work. And now you have to do this without actually collecting data in one place. So this can be a challenging step. And if you don't do it well, biases creep up into your model and end up leading to bad inferences and bad predictions. We've talked a bit about, or at least I've mentioned, security issues, heterogeneity across the different devices, scheduling questions. Today, I'll talk mostly about a direction broadly related to various kinds of errors that can show up while you're training these kinds of distributed machine learning systems. So the high-level sort of motivation is because you no longer control how your machine learning model gets deployed and trained, you're now somehow susceptible to new kinds of failures, sometimes quite different from failures that you might have expected if you're training in a centralized fashion. So some of these failures include hardware failures, which could include bit flip and other kinds of hardware failures during training, software failures like label flips, communication failures like dropped updates. I mention all these to mention one, sometimes there are better, well-established ways to handle some of these failures, and you should use those when you're building distributed systems. However, there are lots of cases where we don't have good models for the failure and we don't have good mitigation strategies. And so we're interested in coming up with machine learning techniques that can remain robust with unmodeled failures. And one way of thinking about unmodeled failures is to try to design for worst case. So there's a broad line of work thinking about Byzantine attacks and sort of worst case attacks and adversarial robustness in this sense. So the idea is that I want to train a machine learning system that still trains in a sort of resilient way to worst case attacks. So there's maybe a cartoon model to maybe motivate this a little bit. You can imagine, say, being at a certain point in a gradient descent, SGD kind of, stochastic gradient descent kind of model training setup. So I'm at a certain point, I get a bunch of gradients. Those gradients roughly all point me in towards the right. So that should be the sort of correct direction on average that my model should update. However, if I have an error or an explicit attack, I can end up pointing exactly in the opposite direction because of this error. And so trying to protect against these kinds of issues is, I think, a key problem in building robust distributed machine learning systems. So the threat model in this settings is under what is known as a parameter server setup. So there's a server and a bunch of workers. The workers are computing with the data that they have locally available without explicitly sharing. Each round, the server sends out some model artifact to all the workers. The workers compute something, typically a gradient update or several gradient updates in a federated learning setup, and then push back the results to the server. The server typically aggregates using averaging and then pushes this back to the workers. And we're worried about, say, a subset of the workers being Byzantine or adversarial or just error prone in various ways. And so one way to try and deal with this is try to sort of deal with it as a robust averaging question. So remember, what the server does is average or aggregates the results from all the different workers. So what is often done is to replace the server average with some kind of robust averaging. And the idea is that if I can replace it with robust averaging, I can show that the sort of overall method has good properties. Specifically, I'll speak a bit mostly about distributed SGD and maybe quickly touch on federated learning settings, a very similar kind of setup. With M workers and N samples by worker per worker. The workers, again, if they're correctly participating in the iterations, send the gradients. If they're faulty, the server has no control over what is sent back from the different workers. And the server's job is to aggregate the results and then take a step in the sort of direction of the aggregated gradients. Now, there's a bunch of work trying to address this problem that is primarily focused on trying to sort of design robust averaging type methods, as I mentioned earlier. So methods, again, like using medians or crumb, where you can show that even with many potential outlier or adversarial workers, the estimate that you get at the end will be close to the population average if there were no attackers or no errors in your system. So this is a good property. However, you can show that this is not enough. And I'll highlight this a bit more in the next slide. But you can show that I can come up with a sequence of updates that are close in terms of Euclidean error, but point in the wrong direction. And with this, I can actually lead a sort of training process to failure. So in particular, I construct an attacker that satisfies the norm guarantees, but is pointed in the wrong direction. So norm guarantees after robust aggregation. And the key takeaway that I want to highlight here is, here I think the important lesson is to focus on learning convergence, not just on sort of the robust averaging aspect of it, but the fact that this is embedded within a broader machine learning system. So just to really to highlight the example, I invite you to take a look at our paper in UAI last year, 2 years ago now, where we look at some of the existing aggregation methods and show, again, this particular failure mode where I can construct attacks that pass the filter and pass all the theory that exists for these methods in terms of being close, getting robust estimates, robustness in terms of close in terms of average, but actually point in the wrong direction, which then leads to failure of the distributed learning procedure. And so our approach to try and mitigate this issue is to use a different kind of robust aggregation, which tries to check particularly if a particular, tries to check if an update is pointing in a good direction or not. So we do this using validation data. We construct what we're calling a stochastic descendant score. This score on the server computes the current point and the update and checks whether the update actually helps the optimization progress or not. It keeps updates that are pointing in a good direction. So if you think about this as sort of pointing towards a good optimal, and it throws away updates that are pointing away. And so it has this sort of radius of confidence where it keeps updates or it throws them away. And we do this by sorting top K scores and keeping the top K. And you can show, I think, reasonable guarantees and how this method might work. The main takeaway, there are assumptions about the properties that the sort of validation data needs to have. And you can show that you also lose some variance because instead of averaging over all of the data workers from, the gradients from all the workers, you're averaging over only the top K. So it reduces some of the convergence rate. Compared to prior work, so additional nice property of this method is it remains fast, but also has tolerance to many more potential attacks. So existing work, you need up to half of your workers to be non-adversarial in order for the aggregation to work. This, in addition to protecting from these kinds of attacks, sort of angle attacks, also has additional tolerance to potentially more of your workers being adversarial. Of course, it does this at the cost of having much more signal and much more work for your server to do in order to check whether updates are valid or not. So it's, of course, a trade-off in terms of both computation and knowledge to get these guarantees. But it has better sort of, the lingo is breakdown point in terms of Byzantine tolerance. So there's a lot of, I think, great other work on this, including work I'll just highlight. There's lines of work that use, say, coding theory, so avoid approximations and just try to get exact results by using redundancy that I'm not going to talk about in detail. So we've done a bunch of experiments. I'm showing here results on here a bit flipping attack. So bits are flipped randomly, comparing the proposed methods to existing methods that use just robust aggregation in a standard way. Here a label flipping attack. So random subset of points have labels randomly flipped, again showing that we can robustly estimate. We can robustly make optimization progress, even at the cost of necessarily updating the gradients exactly correctly. You can extend this idea to federated learning. So using a very similar idea, here's one instantiation, but you can do this many other ways. So we use, again, in our implementation, we use the angle a bit more directly. So I won't belabor the details, but roughly we check whether the angle is within a certain sort of safe range compared using the validation data, keep the angles from the workers that are in the safe range, throw away the ones that are not. And we can, again, show similar kinds of properties. So I'm going to show, just jump straight to results here, showing what these look like for standard data sets here, showing CFAR with ResNet 50 with various kinds of attacks, again, showing that some of the existing methods fail and we are able to make good optimization progress. So again, lots of open questions. We use filtering with the validation data sets. This seems unsatisfying, and we'd like to, I think, improve this. One of the, I think, really interesting aspects of distributed learning, and I think most important, is trying to minimize communication overhead. We've done a bit of work on trying to minimize communication overhead broadly. I think it's still open how these interface with robustness improvement methods. So things like the Zeno method that I just described, combined with communication, reducing communication overhead. We've mostly looked at a parameter server setting. There are lots of other systems architectures, particularly if you're building systems between large data owners, institutions like hospitals. There are many ways that you can build your system architecture. And so we've been trying to investigate various other systems architectures and how robustness interfaces with these other architectures. So I'll summarize. So the key points I talked about today, I talked about metrics showing up in two problems. So first, I talked about algorithmic fairness problems, where we're interested in group fairness notions. I talked about how various notions of group fairness and model measurement can contradict with each other. And I talked about a elicitation method that we are developing actively that is designed to mitigate this by querying stakeholders directly for notions of preference. And I talked about metrics from the point of view of distributed machine learning, different case, where here we're interested in robustness measurements, and pointed out a failure of some of the existing methods that purely look at robust averaging in terms of Euclidean distance, and talked about how different notions of distance might be more appropriate for ensuring robustness in distributed learning. So I'll end here. The broad pitch, again, is that trustworthy machine learning systems are, I think, emerging an important area of how we think about building machine learning systems broadly. We should think about this. Many aspects of this are important. My work has so far mostly focused on the way humans interact with helping us to design measurement methods for thinking about trustworthy ML, by trading off performance and robustness broadly, and how this interfaces with fairness in applications that involve humans. I'll stop here. This is the last slide. I'm happy to take questions.
Let's give a big virtual thanks to Sanmi for a great talk. Well done, Sanmi. And we'll open it up for questions. Lots of questions. I see. Let me see here. Oh, these are claps. Okay, yes. So for questions, you can just turn on your microphone or raise your hand if you want to. See if I can moderate here. All right, while we're waiting for other questions, I had one question, Sanmi. In the first part of the talk, have you done any experiments with real humans in terms of elicitation? How practical do you think that is?
Yeah, so that's active. The current initial results are promising. I can probably say that much reasonably. More than that, it's very much active research.
Thanks. I see we have a question from, I'm not sure who it is, but Michael, maybe? Yes, go ahead. You need to unmute.
Oh, yeah, okay. Is this the correct Michael?
Yes, go ahead.
Okay, sure. So I had a question on when you mention algorithm you use, say you might get different results depending on which algorithm. Would you say that's, I'm not an expert on this, but would you say that's somewhat related to the no free lunch theorem, where some algorithms can perform well in certain scenarios, but they're not going to do well in others? Maybe that's more general, but is this any relation there?
I think that's a reasonable framing of it. I think the key, I think the most important aspect of this, which I think is motivates a lot of this approach, is outside of, again, like really specialized the cartoon cases, you will not get a perfect model, so you have to make trade-offs. And the metric is telling you what trade-offs you want to make. And so we want to understand from humans what trade-offs are appropriate for a certain problem, which we're using to quantify this notion of metric. Because if you could get the perfect model, I guess, perfect accuracy somehow feels like it would just replicate reality. And so there's nothing to do necessarily. Well, let me take that back. So I guess if you had perfect accuracy, then I guess then the issue would be whether you thought that sort of replicating reality was like with the confounds that you could have, say, with data collection and other issues, that whether that result was a good result. Does that make sense? I'm not sure. I'm sort of going.
Yeah, no, that thank you very much.
But I think your thinking in terms of no free lunch, I think, is a good framing of the problem, or a good framing of the motivation for thinking about metrics.
Yeah, thank you. Very, very interesting.
All right, let's see if there's any other questions, maybe from PhD students. Don't be shy. That's a Monday, I guess people are quiet today. Sammy, you mentioned regression as an extension, I think, in the first part of the talk. Could you say just a little bit more about that?
Sure. So yeah, a lot of the framing of the problem so far, so the instantiation that we've pursued the most is very tied to classification problems, because we've thought of most things in terms of confusion matrices, which are really particular to sort of classification decisions. And because we've thought about things in terms of confusion matrices, we've been able to exploit implicit geometry in confusion matrices to design both mitigation methods, which I didn't talk about today, but also elicitation methods that I talked about today. And we don't expect those properties to look the same for other kinds of machine learning problems. And so in some ways, the framework can be generalized, and we've thought a little bit about generalizations. But right now, we think we'll have to sort of case by case it. So if we look at regression, we'll have to look at what are good families of metrics that make sense for regression. How does one instantiate fairness? Algorithmic fairness, group fairness in particular, assuming we mostly are looking at those framings in a regression context, and then try to see if there are properties that make mitigation and potential elicitation sort of efficient, which is one of the bits that we're looking for in these settings.
Thanks. All right, I see we have a question from Lily Cheng. Lily, you want to turn on your microphone, or I can read your question?
Oh, it's a general question about this last page, because you mentioned to enable a trustworthy machine learning system in neuroscience. I'm from neuroscience field, so I'm just really curious, like, where do you think particular needs to improve to have a more trustworthy one? where it's biased. Yeah.
Yeah, so I spent a lot of time in neuroscience work, so I'm also sort of very closely aware of many issues there. So I think for me, the most important is I'm very interested in sort of population analyses and sort of looking at data across lots of different labs and different sites. And like pretty much every other science, definitely all biological sciences, there seem to be strong biases in terms of sort of essentially some signal about the data collection process shows up in the data that you get from each site. And if you don't deal with it, it can lead to confusing outcomes. So there's a story people like to tell, which actually is true in many, there are at least a few anecdotal and real examples of this, where you can take pretty much any scientific data, but let's say neuroscience data for now, and you can set up a classifier to try and predict which PI lab collected the data set, and you'll get really high accuracy. And it's not necessarily for any kind of nefarious reason. They're just maybe differences in data collection processes, differences in population, differences in other kinds of, I guess, context that end up leaving signal in the data. And so if you're interested in broadly any kind of analysis that is across data sets, in my work, I'm thinking about federated learning methods, particularly for understanding brain connectivity across populations. Then you're worried about these kinds of biases as one of the many potential compounds and how these can manifest in your estimates. And it's known that these can have pretty bad issues. So that's what I was referring to.
Thank you.
Thanks. Thanks, Sanmi. I think we're coming up on 2 p.m. here at Pacific time, 5 p.m. your time. So let's give Sanmi another big round of applause, virtual applause here for a great talk.
Thank you.
And Sanmi, we'll have to have you here in person and treat you to dinner. We can't do that virtually, but
that'd be fun.
You're in Southern California. We definitely owe you a dinner and after that talk. Thanks very much.
Looking forward to it. Thank you so much.